is a really powerful resource, actually, that I haven't really talked about. Or you can use it for a variety of things. We'll use it for graphing calculator. And I also want to show you a little bit around Desmos, which is a really, really helpful web graphing calculator that I think some of you might already know about. So I want to do that all in the context of exponential functions. So let me start talking about exponential functions. So here is what an exponential function is. Why am I in purple? That's very strange. So an exponential function is any function of this form, f of x. Oh my God, that's very thick. Hang on a second. What the heck's going on here? How did my preferences change? That's weird. I think I want this. Yeah, it looks better. F of x equals ab to the x, where a and b are going to be numbers, right? 2 times 3 to the x, something like that. It's called exponential because the exponent is a variable. And you might think that maybe doesn't make that much of a difference. Turns out it does. Exponential functions behave quite differently than the functions we've talked about so far, primarily polynomials and linear functions. So just as a quickie example, let's say I have this, f of x equals, we'll do 2 times 3 to the x. Now, according to PEMDAS, we do the 3 to the x first, right? Because that's an exponent first before we multiply. So that's what we're going to be doing. That's where I want to start off. I'm just going to make an XY chart and see what it looks like. So XY, and we're going to see how big this gets. Exponential functions, it turns out, grow really, really fast. So I'm going to do my usual -2, -1, 0, 1, 2. I'm actually going to start with 0 rather than the top or bottom. Just because it's the easiest one to calculate and it'll give us a place to go. And I'll show you what I mean, why we'd want to do that. So if I do f of 0, the variable is going to end up in the exponent. So this is going to be 2 times 3 to the 0. 3 to the 0 is 1, because anything to the 0 is 1. So this is 2 times 1, which is 2. So there we go, 2. Now, I want you to think back to the rules of exponents and the way we discussed exponents working. Whenever you increase the exponent by 1, you are multiplying by the base again. So I'm going to do one all out, but that's what to expect here. So f of 1 is going to be 2 times 3 to the 1, which is 2 times 3 or 6. Right, that's 6. So notice that when we increase the exponent by 1 here, plus 1, this went times 3, right? And that's going to continue to happen. When I increase the exponent by 1 again, I'll do f of 2. And I will get 2 times 3 to the 2. And you can see we've multiplied by another 3 here. So this is 18. Notice this is getting huge in a hurry, right? If we did another one, it would be 54, right? So really big, really quickly. Now going the other direction, of course, that means that we are dividing by 3, right? So if I do f of -1, now I am, remember that negative exponents tell you how many times you are dividing by that number. This is going to be 2 times 3 to the -1, which is 2 times a third, just 2/3. So now we are dividing by 3 every time we go up, and next one we would divide by 3 again, which is probably easier to think of as multiplying by 1/3. So this is going to be 2/9. Right, so getting very small. And as you can imagine, if we continue to divide by 3, the thing that's going to happen is it's going to get smaller and smaller and smaller, but never go below 0. Right, dividing by something can't get you something negative unless the thing you're dividing by is negative, of course. Right, we can just get smaller and smaller towards 0, which we're going to discuss in a second what that looks like and what that means. But this is the basic idea of how to evaluate a exponential function. So I want to show you, well, hang on, I got myself a little outline here. So I want to show you where you can get access to a graphing calculator. So for most of this class, you don't need a graphing calculator or really any calculator, to be honest, for most of it. However, for this section of the course, this group of topics on exponentials and logarithms, you really do. You can't really do this without, or you can't really do these by hand. In fact, like I couldn't do them by hand, for instance. I don't just mean, oh, it would be a challenge for you beginners. That's not what I mean at all. I mean, it's not a thing that you can really do by hand. You need access to a calculator. So let me show you calculator. Now I'm going to go to, let me share up a web page. Where did I go? I put it somewhere. All right, so if I go to VM view, that's what it is. View dot, oh my gosh, I can't type, sbcc.edu. It will take me to this page here, which will give you two choices. One of them is to install a little app on your desktop, or I think on your phone. I think it works on your phone. Or to use the web. Now I use this all the time, so I have the desktop thing installed. So let me show you what this looks like, and then I'll show you what the web app looks like. This right here is just your pipeline username. And it'll bring this up. And these are all of the apps that you can use. Now, these are all on SBCC's servers. So, for instance, you could use this, TI Smart View, which is a calculator, which I'm going to use in a different way. But you can use, this is a graphing calculator. It's a TI-84, I think, is what they've got it set as. You can use Microsoft Word with some add-ons, which are nice, and then a few other things. You can also, if you go to student desktop, I imagine you don't get employee desktop when you log in, but if you go to student desktop, what happens is it turns your computer into effectively a lab computer. Like if you were to go to the math lab, you would, the student desktop is what you would see there. So you can actually treat your computer as though it were a math lab computer, which is pretty neat, right? You can use all the programs that they have there, et cetera, which is, it's basically just these. There might be a few more, I don't know. So yeah, now a word of warning, I'm not going to go through all the details of this. It's a little messy because your computer, when you do this, your computer doesn't know it's your computer anymore. It thinks it's one of SBCC's lab computers. So you can't do things like save conveniently, which is a little awkward. If you're interested, I can show you how to do it. It's not the hardest thing in the world. You just need to save to removable media or to Google Drive or something like that. And then go retrieve it on your, go log back into your computer or close this program and then get it off of your drive or whatever, to get your programs, but it's a little bit awkward. Also, this web app tends to be a little bit buggier than the desktop app. It's also a little bit slow. So I'm going to use the desktop app, and the desktop app is also a little bit slow. So I'm going to have to log into that one. So I'm just going to go ahead and go back to my whiteboard. I'm actually going to pause the recording for a second so that I can log into the calculator, which, like I said, it's a little bit slow. So I'll pause the recording and be right back. All right, it finally logged in. I know it went instantaneously for you, but for me, it's a couple minutes of logging in, which is a little frustrating. But let me show you what it looks like. So here's what we've got. This is the default. I'm gonna turn off this key press history. Hello. There we go, just so we have a little more room on the screen. So this is the TI-84 calculator that we've got. It is, it's called the Ti Emulator, I think. So here's the idea. You get to use your calculator for, this is for free, by the way, if you're on SBCC. If you have an SBCC login, a pipeline login, I should say, you have access to this anywhere you want. Just the way I showed you. So your calculator will do all the things that a regular graphing calculator will do. Like for instance, the buttons I am most interested in are the to the power of buttons. We're going to use that a lot. Also the tables, which are going to be really nice. So a couple things. Let me show you around a little bit, show you what we're going to need. So if I want to do 2 times 3 to the x, or 2 times 3 to the whatever, I would do this. 2 times 3 to the power of, this up caret is exponent. So if I wanted to find 2 times 3 to the 5th, I could do that. I could put, I did 55th, which was not what I intended to do. 2 times 3 to the 5th is not quite that big. Oh my gosh, it's all going wrong. Hang on. 2 times 3 to the power of 5, just 5, not 55. There we go, right? It's a big number, right? Looking back at our not that, but our whiteboard, you can see that that's not all that much bigger than the ones that we did here. 2 times 3 to the second, 2 times 3 to the third, right? So exponential functions get really big really fast, which is why you kind of need a calculator for them, right? They're just too large to be able to do by hand conveniently. So let me introduce you to a little bit of not exactly advanced calculator use, but a better way to use this calculator. So in general, if you want to put a function into this calculator, go to the y equals button and put it in here. This is where your calculator keeps its functions. So it knows, so it can just use the function itself. Like you can just plug things into the function. So let's say I want 2 times 3 to the x, right? So 2 times, what on earth? Oh, my number locks off, pardon me. 2 times 3 to the, and then this is your x key, xt theta n. It's that. No, just one. It's being weird today. I don't know why it's doing this. 2 times 3 to the x. That is my that's my function, right? That's the one that we were graphing. So there's a variety of things that you can do with this, but probably the most useful things at first are going to be make an XY table and graph, right? Those are the things we want to do. And the graphing I'm going to do on Desmos, but I'll show you how to do it here. So if I want to make a table, there's a table button right here. This is a little blue table here. So to get to the blue function here, I have to hit second and then the button. So second and then graph will get me to table. It's registering double clicks. I don't know why. It's being weird. So here I've made the table. You can scroll up and down the table, and it will put in this value for x, and then y1. Remember, our function was called y1. Y1 equals this, and so it's telling you the function output over here. Right, so if I put in -5 for x into 2 times 3 to the x, I would get this number, 0.0082, which isn't the exact number, right? You can see that it's rounding it off, but of course it has to for space. Yeah, so that's one thing you can do. If you want to put in your own number for x, like let's say we wanted to put in a fraction and there's not a fraction available, right? Like what if I want to put in 1.5? How would I do that? Well, here's how you do it. So there is a table set here, which is the second function of Windows. So I'm going to hit that. And that will let me change my independent variable, so the x variable, to ask. So instead of automatically generating independent values of the independent variable, it will ask me for one. So I'm going to hit change that to ask, and then I'm going to go back to table, and it's blank now. Now, you might say that seems bad, but it will let me type in here and put in whatever I want. Right, and so I can put in whatever I want for x, and it will tell me what the y value is. So to do that, I have to have a function in y equals, but then it will let me plug in whatever I want for the x value, which is really nice, right? It's a very convenient way to make an XY table. Like this is how I would make an XY table if I were doing it just for myself rather than trying to calculate everything in my head. The other thing you might want to do is be able to graph. So if I hit graph, what's going to happen is it will make me a graph. Unsurprisingly, there it is. This is what the function looks like. This is what 2 times 3 to the x looks like. And we're going to talk a little bit about where you can see the 2 and the 3 in here, but I'm not going to do it here. So I don't love graphing on this calculator because it's all pixelated and rough, and it's not as good as Desmos, which is the other thing I want to show you. So certainly you can graph on here. To do it, you go to y equals, put in whatever function you want, you hit graph, and it'll graph it for you. Yeah, so I think I want to leave that there and show you Desmos. So let me switch over. Do I have Desmos up? I don't. Hang on one second while I go grab that. I'm gonna stop the share here. This one? Yeah, that one right there. Okay, so let me share that up. This guy. So I made a little Desmos widget. So firstly, this is desmos.com/calculator. Now, this bit right here is this particular graph. I've linked that in the module, so you can access this graph if you want to. So the thing I'm interested in right now is not this or this. So I'm gonna turn those things off. Right now, all I've got is this AB to the x, right? Now, the reason I love Desmos, well, for a variety of reasons, one of the main reasons, it has these sliders. And so I've actually put in AB to the X as my function, and then it lets me specify what A and B are, and I can change them, right? So if I wanted 2 times 3 to the X, I could just slide this over to 2, or I can just type 2, and 2 times 3 to the X, oh, almost, there we go. And this is the function that I saw on the calculator. I can also adjust these things and see how changing those things changes what my function looks like, which is what I'm going to do right now, right? I want to talk about what A and B do to the function, right? What changing A and B do to the function. So here's the thing. Here's the thing I want to point out first. Well, no, let me do this. So here's A. A is the coefficient here. This is not part of the base. The base is B, which is a good reason to call it B. And watch what happens when I change A. So when I change A, it looks like the function is bending, and it sort of is, right? It is kind of bending. But the way I really want to think of it is that it's moving up and down. So when A is, let's say, 2, look where the intercept is. It's at 2, which makes perfect sense, right? Because if X is 0, then B to the X is 1, and the thing you get is just A, right? So when X is 0, which is how you find your Y-intercept, right? You let X be 0 to find your Y-intercept. Then the only thing left in this function is A. And so that's your Y-intercept, right? When A is 3, your Y-intercept is 3, etc. Right? So let's here's 4, right? It's right at 4. Here's 5.3, it's right at 5.3. Right? So A controls the Y-intercept. It sort of not exactly slides, it kind of bends up and down. Which is going to be a little bit confusing when I talk about B. But the way I want to think of A is that it controls the Y-intercept. It controls like how tall my function is, essentially. B, on the other hand, I'm going to move this down a little bit so that we can see. Now, if we think about this for a second, there's going to be some restrictions on A so that this function makes sense, right? So A can be negative, right? You get a function that goes down instead of up if A is negative, right? Negative Y-intercept, or yeah, negative Y-intercept means, well, negative Y-intercept here, unsurprisingly. But if A is 0, then the whole thing just disappears, right? If A is 0, then it doesn't disappear. It's just everything is 0, right? If A is 0, I'm doing 0 times whatever this is, and I always get 0. So in practice, we just don't let A be 0. We just say A can't be 0, even though it theoretically can, right? It can be 0. You just get 0 for everything. You just get kind of a boring function that doesn't really behave like an exponential function. So that's why we disallow it. It's not that it's not that it gives you a domain error or something. We just don't allow it because what you get is just the x-axis instead of something interesting. So we're going to let A be something else. All right, B, your base, controls how fast your function bends. Right? So when B is small, it doesn't bend very fast. And when B is big, it goes up really sharply. Right? You can see that even here, let me zoom out a little bit. Like it kind of looks like that function's going straight up. It's not, right? It's just that when X is even pretty small, Y is huge when B is big, right? That's why it looks like it's going straight up. It's not straight up. It actually goes forever in the X direction. It just goes up really, really fast the whole time when B is big. Oh, that was zooming out. I meant to zoom in. And when B is small, it goes up really shallowly. And so the question I have for you is, what happens when B is 1? Right? It's just A times 1 to some power. Well, 1 to some power is always 1. So when B is getting close to 1, your function is bending up really slowly. So when B is actually 1, the thing you get is a horizontal line. So for that reason, we don't generally allow B to be 1. We generally just say B can't be 1. It's just again, for the same reason that we didn't want A to be 0, right? We don't want to get something boring, and not so much boring, but something that doesn't behave like other exponential functions, right? It doesn't bend at all in either direction. So we just say B can't be 1. And let me go down to 0. Here's what happens when b is less than 1. You can see that we're multiplying by something less than 1 every time, right? My base, as x goes up. Oh, and by the way, just to help your intuition, you want to think of x getting bigger as moving to the right, right? That's where x is getting larger, and so that's the way you, when I say x is increasing, you want to picture what's happening to the graph as it moves to the right. So as x increases here, y decreases. Y is getting smaller because you are multiplying by something less than 1 every time. And so as it gets smaller and smaller and smaller and smaller, and then we get down to 0 here, and let me go on 0. There's 0, and now the function is just it's just the x-axis again, only the positive x-axis, which we'll talk about in a second. But this one will not go negative. You can't have negative bases because of how negative numbers react when they get raised to increasing powers, right? When it's an even power, the negative becomes positive because all the negatives pair up, and you get a positive number. And then when it's an odd exponent, there's an extra negative left over, and you get a negative number, and so it jumps back and forth crazily, and we just don't allow that. It's just too chaotic, and so we don't allow b to be negative. B has to be positive, and also can't be 1, because then it's then you get this horizontal line thing. Yeah, it has to be positive, can't be 1. So bigger than 0, not equal to 1. I'll write that down on the board in just a second. But those are the restrictions, and that's why. It's because we want to classify these functions together. We want to classify functions together that behave alike, right? Like these functions are all kind of alike, so they're all fine. But when a is 0, that's not like the other ones, and so we don't allow that in an exponential function. You just get something that doesn't behave like the other ones. So that's the idea. And like I said, this link will be in the module for you to come and fool around with this all you want. This, by the way, we will talk about this in the next topic. So it's related to this. So I've just put it all in one thing. So you can just go to the one link. All right, let me go back to my whiteboard so I can write down those restrictions. So if I have f of x equals ab to the x, so f of x equals ab to the x. So I need a can be any number except 0, and b has to be greater than 0. So 0 is not allowed because that just gives us 0 to the x, which is always 0. And it also can't be 1, not because that is a problem per se. It just gives us a function that doesn't behave like the other exponential functions, right? We're just multiplying by extra copies of 1 every time, which is not exactly the same as the other functions, so we just disallow it. Okay, so there you go. That's what A and B. That's the restrictions on A and B, and we saw very briefly what A and B do to the graph. I'm going to let you fool around with that in the Desmos link. I've asked a couple questions on homework about like, what does A do and what does B do, and what happens if B is between 0 and 1 versus greater than 1, and what happens if A is negative versus positive. And I will let you kind of hash that out for yourself, but do investigate. It's not particularly complicated. I'll let you figure that all out. So let me hit up my outline. I forgot the next thing I was going to do. Oh yeah, so I wanted to talk a little bit about what these are used for. Now it turns out that exponential functions are super important in applications, because anything that increases by a percentage rather than a fixed amount is an exponential function. So for instance, almost all things in economics and a lot of things in populations like biology and stuff use exponential functions quite a lot, actually. I would say exponential functions are probably the second most important kind of function in all of math, right after linear functions. Yeah, so let's talk a little bit about those. So let's say I have exponential growth. Sort of your basic exponential growth problem. I'm going to do an interest problem here. So let's say I get 5% interest. I earn 5% interest on a bank account. Bank account. I mean, that's actually exceptionally high interest on a bank account, but whatever. We're just going to pretend that I'm some sort of investment genius who managed to earn 5% interest in a bank account. If I start with let's say $1,000, something easy. How much will I have? Sorry, my picture's in the way here. I don't know if you can see me moving that in the video. I think you can't. How much will I have in, let's say, 3 years? All right, so here's the idea. Every year I earn 5% interest. So that means I start with $1,000, 1,000, so year zero. So I started with $1,000. And after 1 year, I have gained 5%. So 1% of 1,000 is 100. No, it's not. That's 10%. 1% of 1,000 is $10. I have gained 5 of those, so I've gained $50 after 1 year. So I'm up to 1,050 after a year. If I want to calculate how much I have in year 2, I'm going to go to calculator. So I will go ahead and go to the TI calculator here. So I wanted to find 1,050 plus 5%. So I want to do 1,050 times 0 or times 0.05. Right, and so this is how much money I gain, plus 52.5, or plus $52.50. It's a little more than last time because I have a little more, right? Instead of 1,000, I have, that's not what I meant to do. Let's try it again. 1050 plus 52.50. All right, there we go. 1102.50. That's how much I have to have after the 3rd year. Now, those of you who know how to do this in one step, I promise I'll show that in just a second. I'm just trying to do this in the simplest possible way. So this is 1102. So this is plus 5%. 5% plus 5%. And year 3, again, we're going to get plus 5%. So I'm going to find 5% of that and add it on. And I'm going to show you how to do that in a better way right afterwards. So it's going to require a little bit of algebra, though. So I want to just kind of finish this off in a simple way. So we've got that 1102.5. So I'm going to multiply that by 0.05. So we get $55.12.5. So we're going to take that and add to plus 1102.50. And so now I've got 1157, let's say 63. $1157.63. That's kind of ugly. Let me fix that up a little bit. Now I'll tolerate a little bit of sloppiness, but that was pretty bad. 1157.63. There we go. Okay, so this is plus 5%. Okay, so after 3 years, I have 1157.63. Great, we solved the problem. Now, that, as you can see, was a little bit tedious. I don't want to do that the same way every time, so let me show you something. So here's what I'm doing. Each time I was doing the amount I started with, so I did 1,000, and then I multiplied that by 5% to calculate the amount of interest I got, right? The first one was 50. And then I added that to the $1,000 that I originally started with. Okay. Here's what I want to do. You might notice there's a greatest common factor between those two terms, right? I'm treating this like a polynomial. There's 1,000 in both of them. I want to factor that out. So this is going to be 1,000 times 0.05 plus 1. Right, but 0.05 plus 1 is just 1.05. So if I do 1,000 times 1.05, that will get me whatever it was, 1,050. All right, so if I then take, so this is 1,050. If I then take that and I want to add 5% to it, well, I would do the same thing, right? I would do 1050 times 0.05 plus 1050. And I would do the same thing. I factor that 1,050. That's 1,050 times 1.05 in exactly the same way as it was before. And then if I want to do the next one, I would do 1,000, 1,000, or what was it, 110250 times 1.05. But what you might notice is that this can just replace that. So what I've really got here is the following. I really have, I'm just going to do this in red. I really have 1,000 times 1.05 times 1.05, right? Which is just 1,000 times 1.05 to the second. So every time I want to add 5% to whatever amount I had, that's the same as multiplying by 1 plus 5%. That's where the exponential part comes in. So if I want to write down, if I want to give a formula for the amount of money in my bank account, so let's say A of t. So the amount of money at time t is equal to the starting amount of money, which is, it's called principal, but I'm going to call it A0 because this actually works for anything, times 1 plus the growth rate, that's R in decimal, to the t power. A0 equals starting amount. R equals growth rate. And t equals time. Now, very often t is given in years, but not always. Sometimes it's given in hours or even seconds, depending on what's growing. This is the formula not just for interest, but also for population and also for decay. If your growth rate is negative, this works. So just R is a negative number, and this will something that's decaying away exponentially. Which happens actually quite a lot as well. We're going to do an example with what I'm trying to say here, nuclear decay in a little bit, but R can be either positive or negative. This is not just for money. That's why I didn't call this P. I called it A0 for like starting amount. The zero, don't think of the zero as like multiplying. It's just a subscript to identify that it's like starting at time 0, basically. So this is your exponential growth formula. It's also a good formula for exponential decay. We'll get into that a little bit later. Maybe not in this video. So the way I would write my bank account problem is I would say that the amount in the bank account at time t was equal to $1,000, my starting amount, times 1.05 to the t, where t is the number of years that I'm asking for. So if I wanted to do this the easy way, I would go back to my bank account problem here, and I would, so 1157.63 was my answer. So instead of doing that in 3 steps, what I would do is I would just put 3 in here for t. I would use this function and put in 3 for t. So let's see how that looks. So I'm just going to do 1,000 times 1.05 to the power of 3, and lo and behold, there's your answer. So back to whiteboard. In general, if you know that something is growing or shrinking exponentially, this is the formula. This is the basic formula you want to use. We'll maybe build on this a little bit in the future. We will definitely build on this a little bit in the future. But this is your basic exponential formula. A of t equals A0 times 1 plus r to the t. And that comes out looking something like this, right? It's starting amount times 1 plus your growth rate to the power of the number of times you are counting the growth. So there's a variant on this that is often used in nuclear decay and other things, actually. It's called half-life. So let me show you how that works. So this guy's going to be half-life. It's the same sort of thing, just expressed differently. So let's see, carbon-14. So you guys have probably heard of carbon dating before. So let me explain how carbon dating works very briefly so that you know exactly what's going on here. In a very old organic thing, or in any organic material that takes in air, there's a certain amount, or there's a certain percentage of carbon that is well known to be the radioactive variant, carbon-14. Now, radioactive decay, I guess I have to explain that too. So the way radioactive decay works is periodically a radioactive material will give off a particle called an alpha, beta, or gamma particle, depending on what kind of material you have. And when it does that, it's actually shooting off like a little proton. It's shooting off a little atom, basically. I think alpha particles are hydrogen atoms, beta particles are helium atoms, and gamma particles are something I don't know. But basically, it shoots off a little piece of the atom, or a little piece of the molecule, and that changes it into something else. So what happens with carbon-14 is it will periodically shoot off one of these particles, I don't remember which one, and turn into something else. The more atoms you have, the more radiation they emit, and the faster they change into some other particle. What this means is that there's a fixed time by which about half of them will have done this, called the half-life. So what half-life is it's the number of, or it's the amount of time that it takes for half of something to decay away, in this case, a radioactive element. Carbon-14 is a radioactive element. It will get into your body, it's in your body right now, and the body of every other living thing on Earth. When you die, it stops getting pulled into your body because it gets pulled in for humans and other breathing organisms. It comes into your body when you breathe, right? It's part of the air. And so when you stop breathing, you stop pulling it in and it just decays. So what you can do is take the fraction of carbon in something and figure out how much of that is carbon-14 and how much of it is regular carbon. And since the global proportion of carbon-14 is well known, although I don't personally know it because I'm not a biologist or an anthropologist, archaeologist, I don't know, whoever studies old things, paleontologist, something in there. Because that percentage is known, however much it's less than that percentage is in the remains that you're studying, will allow you to figure out how old this thing is. That's what carbon dating is you're figuring out how old something is or how long ago something basically stopped taking in carbon-14 by how much less carbon-14 it has now than you would expect it to have if it was currently alive today. That's carbon dating. That's how scientists figure out how old things are. This is also, by the way, why you can't be super precise about when something died. Like this, on very long time scales like this, and with very tiny percentages like we're dealing with, it's very hard to be precise. So here's how this works. Now we've got our physics lesson over. Here's how this works. Carbon-14 has a half-life. Half-life of 5,760 years. That means that after 5,760 years of just sitting there, carbon-14 will have lost about half of its original mass. So what we can do is this. We can say that the percentage of carbon-14 at time t, percentage of the original amount at time t is P0 times, well, every 5,760 years, it decays, half of it decays away. So every 5,760 years, we are multiplying by another copy of a half. Now, we don't want to do this every year, so I don't want to do just t here, right? If I put t here, then I'm saying that I multiply by a half every year, but I don't want to do that. I want to multiply by a half every 5,760 years. I'm going to do this, 5760, like that. Now, the starting percentage is 100% of what we would expect. So for carbon dating and for, what do I want to say here? For any sort of radioactive decay problems, there's kind of two variations that you're going to do. One is the percentage version, which I've got here, right? So P of T, the starting percent is 100%, is 100 times a half to the T over half-life. That's the percentage. Or there's also the amount version, which is very similar to the one we just did, or to the interest problem we just did. So, or we could have this, A of T is A0. So now we don't know what the starting amount was, right? It could be anything, but this part still remains the same. I don't know why I'm doing my fraction bars differently, but there you have it. Something like that. So on your homework, I have a carbon-14 problem, I think. But the basic idea is this is the formula you want to make. If you're doing a percentage version, start with 100 and then do a half to the T over half-life. And if you're doing an amount version, then start with the amount, probably in grams, or milligrams or micrograms or whatever. Radioactive elements tend to be pretty small, times 1/2 to the T over half-life. So let me do a quickie example. We'll just make one up real fast. So what percent of carbon-14 remains after, let's say, 3,000 years? All right, well, I'm doing the percent version, so I'm going to say that P of T is 100 times 1/2 to the T over 5760, where T is the number of years. So what I've got here is that P of 3,000 is 100. That's not, I didn't write the thing I said. 100 times 1/2 to the 3,000 over 5760. So it's problems like this that were why I was saying you really need a calculator. Like, this is not a thing you can do in your head. It's not a thing that anybody can do in their head, as far as I know. So let's go pop into the calculator and do that. So I'm going to do 100 times 0.5 to the power of 3,000. Let's put this in parentheses, 3,000 over 5760. And you could certainly find 3,000 over 5760 first and just put it in like that. There we go. 60. Oh, interesting. 169. That was not intentional. 69.7%, let's just say. So go here. So it's about equal to 69.7%. So whatever remains, or however much it started with, about 69.7% is left after 3,000 years. Let's do the same thing, but I want the amount version, just so you can see how they are similar and different. Oh, come on, toolbar. Sorry, it's not letting me make a new one. So if we start a let's say 1.3 gram sample of C14 has been around decaying for, I don't know, 1,500 years. How much is left? So we're going to do the same thing, basically, except now I've got an amount question instead of a percent question. So I'm going to start with my amount. So I'm going to go A of T is a 0 times 1/2 to the T over half-life, so 5760. So here I've got A of T equals 1.3 times 1/2 to the 1500 over 5760. I'm just going to go jam that into the calculator and see what I get. Calculator, where are you at? So we're going to go 1.3 times 0.5 to the power of, let's put it in parentheses again, 1500 divided by 5760, and see what we get. I got 1.085 grams left. About equal to 1.085 grams. So you can see it's decaying away, but very slowly, right? It's been 1,500 years. 1,500 years ago, just for reference, was the Dark Ages, maybe even slightly before that. No, it's about the Dark Ages. So yeah, this 1.3 grams of carbon-14 has been decaying away for 15 years, and it's lost about, 0.29 grams, something like that, or 0.21 grams. So there you go. That's how you evaluate these functions. Be on the lookout for anything that's changing by a percentage. If that's the case, you probably got an exponential function, and as you can imagine, that's a lot of stuff that changes by percentages every year. And I think that is all I wanted to say. Let's just make sure that I've hit everything. Yeah, applications was the last thing, so fantastic. So I'm going to go ahead and stop the video now. It is already plenty long, and I will see you guys in the next one.